The grandfather's paradox we're exploring is one that sounds simple, but has tortured physicists for over a century. Stick around as it strikes at the very heart of causality itself. Picture this. You're a brilliant inventor who's just built the world's first time machine. Excited to test your creation, you decide to travel back to the year 1925 to witness the golden age of jazz firsthand. You arrive in New York City, marveling at the vintage cars and the fashion. But then something goes terribly wrong. While walking down a bustling street, you accidentally bump into a young man crossing the road. He stumbles backward, directly into the path of an oncoming automobile. The impact is fatal. Only later do you realize the horrifying truth. That man was your grandfather, and you've just prevented him from ever meeting your grandmother. Here's where logic begins to eat itself alive. If your grandfather dies before having children, your parent is never born. If your parent is never born, you certainly aren't. But if you were never born, you couldn't have built the time machine. You couldn't have traveled back in time. Your grandfather would have lived, met your grandmother, and eventually led to your birth, which means you could build the time machine and travel back to kill him all over again. It's an infinite loop of contradiction that makes reality short-circuit. Every effect needs a cause, but here the effect seems to destroy its own cause. This paradox has spawned countless theories, each more mind-bending than the last. Some physicists argue that the universe would conspire to prevent such paradoxes. Your gun would jam at the crucial moment. You'd slip on a conveniently placed banana peel. The laws of physics would bend reality itself to maintain consistency. Others propose that killing your grandfather wouldn't erase you from existence. Instead, it would split reality into parallel universes. You'd create a new timeline where you never existed, but you'd remain stranded in that alternate past as a temporal refugee from a reality that still exists but can never be reached again. The second paradox takes us from the personal to the cosmic, and it's even more unsettling. It's called the Fermi paradox, named after physicist Enrico Fermi, who posed a deceptively simple question during a lunch conversation in 1950. Where is everybody? Look up at the night sky. You're seeing just a tiny fraction of an incomprehensibly vast universe. Our observable universe holds galaxy alone, contains hundreds of billions of stars. The trillions of galaxies. Many of those stars have planets orbiting in zones where liquid water could exist. The universe has been around for nearly 14 billion years, providing ample time for life to evolve and spread. Given these staggering numbers, intelligent spacefaring civilizations should be everywhere. Even if just a tiny percentage of planets developed life, and an even tinier fraction of those developed intelligence, and an impossibly small fraction of those achieved interstellar travel, the galaxy should still be teeming with alien activity. A civilization just slightly more advanced than ours could send self-replicating probes to every star system in the galaxy within a few million years. So where are the radio signals? Where are the megastructures? Where is even a single piece of alien garbage floating through space? The silence is deafening and terrifying. This absence of evidence points to something called the Great Filter, a hypothetical barrier so difficult to overcome that it prevents almost all life from reaching an advanced stage. The nightmare scenario is that this filter lies ahead of perhaps us. Every civilization inevitably develops technology that destroys them. Nuclear weapons, runaway climate change, malevolent artificial intelligence, or nanotechnology disasters that consume everything. If this is true, the cosmic silence isn't empty space. It's a graveyard filled with the remains of countless civilizations that couldn't overcome the same challenges we're facing right now. We might be approaching a wall that no species has ever successfully climbed. But there's an even more chilling possibility. What if the universe is full of intelligent life, but everyone is hiding? In what scientists call the dark forest hypothesis, broadcasting your location to the cosmos is essentially cosmic suicide. Any civilization that announces its presence risks being eliminated by a more advanced, more paranoid species that views all other life as a potential future threat. The silence, then, isn't emptiness, it's fear. Every intelligent species in the universe might be holding its breath, terrified to make a sound, because they know something is listening in the darkness. Our third paradox seems almost childishly simple, yet it reveals the fundamental structure of the cosmos itself. It's called Olbers' paradox, and it asks a question that should keep you awake at night. Why is the night sky dark? Think about it logically. If the universe is infinite in size, has existed forever, and contains a roughly uniform distribution of stars, then every single direction you look should eventually end at the surface of a star. It would be like standing in an infinitely large forest where every line of sight terminates at a tree trunk. This means the entire night sky should be a continuous blazing sheet of light, as bright as the surface of our sun. There should be no darkness anywhere. Day and night would be indistinguishable, both seared by the light of infinite stars. Yet we know this isn't the case. We can see darkness between the stars. We experience night. This simple observation completely destroys the idea of an infinite, eternal, static universe. The solution to this paradox is one of the most powerful pieces of evidence for the Big Bang theory and our modern understanding of cosmology. The universe isn't infinitely old. It began approximately 13.8 billion years ago, which means we can only see light from stars whose signals have had enough time to reach us. Light from stars 20 billion light years away simply hasn't arrived yet, leaving those patches of sky dark from our perspective. Even more importantly, the universe isn't static. It's expanding at an accelerating rate. This expansion stretches the wavelengths of light, traveling through space, shifting radiation from distant galaxies into invisible parts of the spectrum. The most distant objects are receding so fast that their light will never reach us at all. The darkness above our heads isn't empty space. It's the shadow of cosmic expansion and the ghost of the Big Bang itself, proving that the universe had a beginning and revealing the dynamic nature of reality on the grandest possible scale. These first three paradoxes are just the beginning. We've barely scratched the surface of the contradictions and impossibilities that lurk within the fabric of existence itself. Each one challenges our most basic assumptions about time, space, causality, and consciousness. The fourth paradox brings us into the bizarre world of quantum mechanics, where common sense goes to die. It's called Schrödinger's cat, and it's simultaneously the most famous and most misunderstood thought experiment in all of science. This paradox doesn't just challenge our understanding of physics, it questions the very nature of reality and observation. Picture a diabolical setup conceived by physicist Erwin Schrödinger in 1935. You place a cat inside a sealed, windowless box. Alongside the cat sits a tiny amount of radioactive material, precisely calibrated, so there's exactly a 50% chance that one atom will decay within an hour, and a 50% chance that none will. This is purely random, governed by the strange laws of quantum mechanics. Connected to this radioactive sample is a Geiger counter. If it detects radiation from a decayed atom, it triggers a hammer that smashes a vial of deadly poison, killing the cat instantly. If no decay occurs, the vial remains intact and the cat stays alive. You seal the box and wait 1 hour. According to our everyday experience, the cat inside must be either alive or dead. We simply don't know which until we open the box. But quantum mechanics laughs at our intuition. According to the Copenhagen interpretation, until the system is observed, the radioactive atom exists in something called superposition. It's not decayed or undecayed. It's simultaneously both states at once, suspended in a haze of probability. Since the cat's extricably linked to the atom, fate is in state. This implies something absolutely insane. The cat itself must also be in superposition, Until you open the box and observe the system, the cat is both 100% alive and 100% dead at the same time. Schrödinger wasn't proposing this because he enjoyed torturing imaginary cats. He was demonstrating how ridiculous the Copenhagen interpretation becomes when applied to large objects instead of subatomic particles. How can something be simultaneously alive and dead? It violates every instinct we have about reality. The act of observation supposedly forces the universe to choose. The moment you lift the lid, the wave function collapses, the superposition breaks, and the cat instantly resolves into either a living or dead state. But this raises even deeper questions. What constitutes an observation? Does it require a conscious human mind? Would a security camera count? What about a mouse in the box? This is called the measurement problem, and it strikes at the heart of reality itself. Are we passive observers of an objective universe, or do our observations actually create the reality we experience? Our fifth paradox takes us on a journey through space-time that will make you question the nature of aging itself. It's called the twin paradox, and it emerges from Einstein's theory of special relativity, which revealed that time is not the absolute constant we assumed it to be. Imagine identical twins named Sarah and Michael. Sarah remains on Earth, living an ordinary life. Michael, seeking adventure, climbs aboard an advanced spacecraft and system. His embarks on a journey to a distant starship, travels at 99% the speed of light. After several years of travel, he turns around and returns to Earth at the same incredible velocity. When Michael steps out of his spacecraft, something shocking has occurred. Due to a phenomenon called time dilation, time passed more slowly for Michael during his high-speed journey. He has aged only a few years, but his twin sister Sarah has aged several decades. Michael has effectively travelled into the future, leaving his sister behind in time. This isn't science fiction. It's been confirmed with atomic clocks flown on airplanes and satellites. Time genuinely runs slower for objects moving at high speeds relative to stationary observers. But here's where the paradox kicks in. From Michael's perspective, inside the spacecraft, he was stationary. It was earthomed away that zoe from him at tremendous speed and then returned. If all motion is relative, shouldn't time have slowed down for Sarah instead? Both twins observe the other as the one moving, so both should predict the other will be younger. The resolution lies in a crucial asymmetry that breaks the apparent contradiction. Acceleration. Sarah remained in essentially the same reference frame throughout the entire experiment. Michael, however, had to accelerate to reach his travelling speed, decelerate and turn around at the distant star, then accelerate again to return to Earth. These accelerations fundamentally distinguish his journey from Sarah's stationary experience. It's the twin who accelerates, who switches between different reference frames, who experiences less time. The paradox dissolves, but it leaves us with a profound realization. Time itself is malleable, dependent on motion and gravity in ways that shatter our intuitive understanding of temporal flow. The sixth paradox brings us to one of the oldest puzzles in human thought, yet its implications remain as mind-bending today as they were 2,500 years ago. These are Zeno's paradoxes, created by the ancient Greek philosopher Zeno of Elea to demonstrate that motion itself might be an illusion. Consider this scenario. You want to walk across a room to reach the opposite wall. Simple enough, right? Not according to Zeno. To complete your journey, you must first travel half the distance. But before you can travel that half, you must first cover half of that distance, which is a quarter of the total. And before covering the quarter, you need to traverse half of that, an eighth of the room. This process of halving distances continues infinitely. You can divide any distance an unlimited number of times, creating an infinite sequence of smaller and smaller segments. To reach your destination, you must complete an infinite number of individual journeys. But how can anyone finish an infinite number of tasks in finite time? it seems logically impossible. Zeno concluded that motion must be an elaborate illusion. You can never truly reach your destination because you can never even take the first step. Another version involves the legendary warrior Achilles racing a tortoise. Even if Achilles runs 10 times faster, if the tortoise gets a head start, Achilles can never overtake it. By the time he reaches the tortoise's starting position, the tortoise has moved slightly ahead. By the time he covers that new distance, the tortoise has advanced again. The gap shrinks but never closes completely. These paradoxes tormented brilliant minds for over 2,000 years because they expose our discomfort with infinity. Our brains aren't equipped to intuitively grasp infinite processes. The solution finally emerged with the development of calculus, which revealed that infinite series can have finite sums. Yes, crossing the room requires completing infinitely many steps, but these steps become progressively smaller. The mathematical series 1/2 plus 1/4 plus 1/8 plus 1/16 continued forever doesn't add up to infinity. It converges perfectly to exactly 1. Similarly, the time required for each step decreases proportionally, allowing infinite tasks to be completed in finite time. Zeno's paradoxes don't prove motion is impossible. They prove that reality operates according to the subtle mathematics of infinity, whether our intuition can grasp it or not. Our seventh paradox ventures into the realm of time travel once again, but this time it creates something even stranger than grandfather-killing contradictions. It's called the Bootstrap Paradox, and it describes objects, information, or even people that have no discernible origin. They exist in closed loops with no beginning point. Here's a classic example that will twist your mind into knots. A devoted music lover builds a time machine specifically to meet his hero, Ludwig van Beethoven. He travels back to 18th century Vienna, carrying with him complete sheet music for all of Beethoven's symphonies, sonatas, and concertos. But when he arrives, he makes a horrifying discovery. There is no Ludwig van Beethoven. The composer never existed. Panicked that a world without Beethoven's masterpieces is intolerable, the time traveler decides to publish the music himself under the name Ludwig van Beethoven. The compositions become famous, inspiring generations of musicians and eventually motivating our time traveler to journey backward in the first place. The question that will keep you awake tonight is this: who actually wrote the music? It wasn't the historical Beethoven because he never existed. It wasn't the time traveler because he merely copyworks. That existing musical information seems to have materialized from thin air, creating itself in a causally impossible loop. This gets even stranger when applied to physical objects. Imagine an inventor creates a unique pocket watch, then uses time travel to give it to his younger self. The younger version keeps the watch throughout his life, aging into the inventor who eventually gives it to his own younger self. The watches pass through an endless loop, but when was it actually manufactured? Who built it? The object appears to have existed forever, never created, only transferred. This violates fundamental laws of physics, particularly entropy. Objects should deteriorate over time, accumulating wear and damage. A pocket watch cycling through infinite loops should be an unrecognizable pile of rust and fragments, not a pristine timepiece. The Bootstrap Paradox suggests either such causal loops are physically impossible, or our understanding of causality is fundamentally incomplete. Perhaps in the strange logic of time travel, information and objects can exist without creators, floating freely in the currents of looped space-time, defying every intuition we have about cause and effect. Our eighth paradox drags us into the most extreme environments in the universe, where the fundamental laws of physics collide in ways that threaten to shatter our understanding of reality itself. This is the black hole information paradox, and it's been tearing theoretical physics apart for decades. Here's the setup that has kept brilliant minds awake at night. Modern physics rests on two pillars that have never failed us. General relativity describes gravity and the large-scale structure of space-time with breathtaking precision. Quantum mechanics governs the microscopic world of atoms and particles with mathematical elegance. Both theories work flawlessly in their respective domains, but when you force them into the same room, they start a fight that could destroy physics itself. According to Einstein's general relativity, a black hole is the ultimate prison. Its gravitational field is so intense that nothing, not even light, can escape once it crosses the event horizon. Information that falls into a black hole is trapped forever, sealed away from the rest of the universe behind an impenetrable barrier. But quantum mechanics has an iron never been broken, information-clad rule that cannot be destroyed. Ever. You can burn a book, but the information about every atom in that book still exists, scattered among the smoke particles, ash, and heat radiation. You can scramble information beyond recognition, but you can never erase it completely from the universe. So what happens when you throw that book into a black hole? The information describing every molecule crosses the event horizon and vanishes from our observable universe. According to relativity, it's gone forever, locked behind the ultimate barrier. But this directly violates quantum mechanics' fundamental principle. The plot thickens when we consider Stephen Hawking's revolutionary discovery. Black holes aren't completely black. They slowly leak radiation over immense periods of time, gradually losing mass until they eventually evaporate completely. After trillions upon trillions of years, the black hole disappears, leaving nothing behind but a faint whisper of radiation scattered across space. If the black hole evaporates entirely, what happened to the information from that book you threw in? Is it destroyed forever, proving quantum mechanics wrong? Or does it somehow escape, encoded in the Hawking radiation, proving that general relativity's description of black holes is fundamentally flawed? This isn't just an abstract puzzle for ivory tower theorists. It's a crisis that strikes at the heart of our quest to understand the universe. You can't have it both ways. Either information can be destroyed, shattering quantum mechanics, or black holes aren't the perfect prisons we thought they were, demolishing our understanding of gravity and space-time. Proposed solutions read like science fiction. Some physicists suggest the information is encoded in subtle quantum correlations within the seemingly random Hawking radiation, like a secret message hidden in static. Others propose the holographic principle, arguing that all the information about the black hole's three-dimensional interior is actually stored on its two-dimensional event horizon surface, like a cosmic hologram. This radical idea has been extended to the entire universe, suggesting that our three-dimensional reality might be nothing more than a holographic projection of information stored on a distant two-dimensional surface. The book never really falls into the black hole. Its information is smeared across the event horizon, creating the illusion of a three-dimensional interior. The black hole information paradox isn't just about exotic objects in distant space. It's a CL of space, time, and reality that our entire conception might be fundamentally wrong. Our ninth paradox brings us back to the quantum realm, but this time it reveals something deeply disturbing about the relationship between observation and reality. It's called the observer paradox, and it suggests that the act of measurement doesn't just reveal properties of the universe, it actually creates them. In everyday life, we assume that objects have definite properties whether we're looking at them or not. A red car is red, even when nobody's watching it. A baseball has a specific location and velocity, even when it's hidden in a box. These seem like obvious truths, but quantum mechanics laughs at our assumptions. At the subatomic level, particles don't exist as tiny definite points with precise locations and velocities. Instead, they exist as wave functions, ghostly clouds of probability that represent all possible states simultaneously. An electron isn't in any specific place. It's in all possible places at once, spread across space like a quantum fog. The paradox emerges when you try to measure this particle. To find out where the electron is, you must interact with it, perhaps by bouncing a photon of light off it. The moment you do this, the moment you observe it, something extraordinary happens. The wave function collapses instantly. The cloud of probability vanishes, and the electron is forced to choose a single definite location. Your measurement hasn't just revealed where the particle was, it has fundamentally altered the particle's state, transforming it from a wave of potential into a concrete reality. The very act of observation has changed the system you're trying to study. This leads directly to Heisenberg's uncertainty principle, which states that there are fundamental limits to how precisely you can know certain properties of a particle simultaneously. The more accurately you measure an electron's position, the less accurately you can know its momentum, and vice versa. It's not because our instruments are crude or our techniques are flawed. It's a built-in feature of reality itself. The universe has intrinsic fuzziness at its most fundamental level. You can ask where a particle is and get an answer, or you can ask how fast it's moving and get an answer. But you can never get precise answers to both questions simultaneously. Measuring one property inherently scrambles information about the other. This raises profound questions that philosophers and physicists are still grappling with. What constitutes a measurement? Does it require a conscious observer, or does any interaction with the environment count? If observation creates reality rather than revealing it, what does that say about the nature of existence itself? The observer paradox suggests that we're not passive spectators watching the universe unfold. We're active participants whose very attempts to understand reality help to create the reality we experience. The boundary between observer and observed dissolves, leaving us in a participatory universe where consciousness and physics are inextricably intertwined. Our 10th and final paradox is the most existentially terrifying of all. It doesn't just question the laws of physics or the nature of time. It questions whether anything you've ever experienced is real. This is the simulation argument, and it suggests that one of three deeply unsettling propositions must be true. The argument, most famously articulated by philosopher Nick Bostrom, doesn't claim we're living in a computer simulation. Instead, it presents a logical trilemma where at least one of three possibilities must be correct, and two of them are genuinely terrifying. Proposition 1 is the extinction scenario. Civilizations at our current level of technological development almost always destroy themselves before they become capable of creating realistic simulations of their evolutionary past. We're heading toward nuclear war, climate catastrophe, artificial intelligence disasters, or some other catastrophic filter that will wipe us out before we ever reach the simulation building stage. Proposition 2 is the disinterest scenario. Advanced civilizations that do survive to technological maturity have absolutely zero interest in running ancestor simulations. Perhaps they consider it unethical to create conscious beings capable of suffering. Maybe they've transcended to higher forms of existence and find simulating their primitive past utterly boring. For whatever reason, they possess the capability, but universally choose not to use it. Proposition 3 is the simulation scenario, and it's where things get genuinely disturbing. If civilizations do survive and they do run ancestor simulations, then we are almost certainly living inside one of those simulations right now. The logic is coldly statistical. A single advanced civilization could run billions or trillions of detailed simulations of their evolutionary history, each containing billions of conscious simulated minds like ours. If this happens, the number of simulated realities would vastly outnumber the single base reality. The population of simulated minds would be astronomically larger than the population of real biological minds. If that's true, from which population are you more likely to have been randomly selected? The tiny group of real beings in base reality, or the incomprehensibly larger population of simulated beings across countless digital worlds? The mathematics are stark. If advanced civilizations create ancestor simulations, The odds are overwhelming that any given conscious mind, including yours, is one of the simulated ones. Your entire existence, every memory you cherish, every relationship you value, every experience that defines who you are, could be nothing more than lines of code running on some post-human computer. This is the ultimate paradox of existence. Our very ability to contemplate this question, to wonder about the nature of reality, could be evidence for our own unreality. If we eventually develop the technology to create our own ancestor simulations, it would be almost definitive proof that we ourselves are trapped inside one. Are there glitches in the matrix we can detect? Strange coincidences, physical constants that seem suspiciously fine-tuned? Or is the simulation so perfect that it's indistinguishable from reality by definition? And if it is indistinguishable, does the distinction even matter? The food still nourishes you, the love still feels real, the pain still hurts. But somewhere in the back of your mind, a nagging thought persists. This entire universe, every star you've ever seen, every person you've ever loved, every thought you've ever had, might be nothing more than an elaborate digital dream running on some unimaginably advanced computer. These 10 paradoxes reveal the shocking truth about reality. The universe is far stranger, far more counterintuitive, and far more mysterious than our everyday experience suggests. From the grandfather paradox to the simulation argument, each contradiction exposes the limitations of human intuition and the profound depths of cosmic mystery. But perhaps that's exactly as it should be. A universe simple enough for human minds to fully comprehend might not be a universe worth inhabiting. The paradoxes don't just challenge our understanding. They remind us that reality is an ongoing mystery, always deeper and more wonderful than we dare to imagine. The next time you look up at the night sky or contemplate your own existence, remember these paradoxes. They're not just intellectual puzzles. They're windows into the fundamental nature of existence itself, revealing that the universe is not only stranger than we suppose, but stranger than we can suppose. Reality, it turns out, has been questioning us all along. These 10 paradoxes represent more than intellectual curiosities dreamed up by scientists with too much time on their hands. They're cracks in the foundation of everything you thought you knew about existence. Each contradiction reveals that reality operates according to rules so bizarre, so counterintuitive, that our everyday experience becomes nothing more than a comforting illusion. The universe isn't just stranger than we imagine, it's stranger than we can imagine. And that terrifying, beautiful truth should change how you see everything forever.